started.
Let's see. Let me start by correcting something that I said that wasn't quite right in the problem session. I said that sigma I, sigma j was I epsilon ijk summed k equals 1 to 3 sigma k. That's correct if I is not equal to j, but there's also a delta function, not a delta function, a Kronecker delta. That is to say, sigma 1 squared is equal to sigma 2 squared is equal to 3, sigma 3 squared is equal to 1, which is the 1 by 1, the 2 by 2 unit matrix. So I just was focusing on the case of I not equal to j in the problem session. The sigmas are the Pauli matrices that are defined on one of the early pages of the handout. So a set of vectors v1, vn are linearly dependent if there are numbers not all 0 such that 0 is equal to C1 V1 plus C2 V2. So if you can find non-zero numbers such that that sum is equal to 0, then they're linearly dependent, and a set of vectors vi is linearly independent simply if it's not linearly dependent. So the key definition is linear dependence means that you can find a vector that isn't 0, you dot the vector into the vectors in question, and the sum adds up to 0, and not all the c's are 0. That's linear dependence. Linear independence is if you're not linearly dependent. If you have a set of vectors that's linearly independent, then it spans the space, because if you that is to say, you can write any vector u as C1 V1 plus. That is to say, if the v's are linearly independent, then you can write any vector in the space this way. The idea is that any additional vector would make the set linearly dependent. So in other words, a set of vectors that is linearly independent is maximal in a vector space if the addition of any extra vector to it makes it linearly dependent. And so the key thing here is maximal, or maximally. So a maximally linearly independent set is one such that if you add any vector to it, it becomes linearly dependent. The set becomes linearly dependent. And so in that case, you can write any vector in the vector space in terms of a maximally linearly independent set of vectors. And the reason is that if you did have this extra set, then it would be linearly dependent, so you'd be able to write C0U plus C1V1 plus CNVN, and these guys would be, not all the C's would be 0, and in particular, these guys, this one, you can divide through by, and then you get this, you can express the U in terms of simply the V's. So basically a maximal set of linearly independent vectors is complete in the vector space, and the number of vectors in a maximally linearly independent set is the dimension of the space. So if n is the number of vectors in a maximal set of linearly independent vectors, then that set is of course linearly independent because it's maximal, it's complete, and n is the dimension of the space. So that's the basic idea of dimension of the space, and intuitively we understand that in a plane one can imagine those two vectors as linearly independent, or you can take two vectors like that as linearly independent, and by taking linear combinations of these vectors we can represent any point in the space. If one adds another dimension, so it's 3 dimensions, then you need a third vector to make a linearly independent set, and if you have 3 linearly independent vectors in 3 dimensions, that's a maximal set of linearly independent vectors. Is there a question? I normally give candy to the person who names them. Do you want a candy?
Yes. Thanks.
Now, orthonormal vectors. The idea is that orthonormal vectors are vectors whose inner product is 1 if the vector is the same and it's 0 otherwise. And one might start with some vectors vi that are, say, linearly independent, but not orthonormal. So they can form, if it's a maximal set of linearly independent vectors, then they can form a basis for the vector space. But in general, the basis will be composed of vectors that aren't orthogonal, and aren't normalized. And there's a standard way of taking a basis. Yeah, that's something that since I'm not reading this, let me just emphasize what the word basis means. A basis for a vector space is a maximal set of linearly independent vectors in the vector space. So it's a complete set of vectors in the basis, in the vector space. That's another term, another meaning of the word basis, a shorter meaning of the word basis. It's a complete set of vectors in the vector space. So suppose we have a basis for a vector space. It's nice to have an orthonormal basis, where all the vectors have unit length and they're all perpendicular to each other. So that, for example, in 3-dimensional space we talk about I, j, k, or sometimes I hat, j hat, k hat. We all like those vectors because then we can compute things much more easily. Now there's a standard way of taking a basis and making it orthonormal, and this is called the Gram-Schmidt method. And there are, of course, at least 6 ways of spelling Schmidt. You leave the C out or you leave the D out. And let me say what we're doing then. So let's start with a basis VI. And we're going to go to an orthonormal basis UI. Well, the first one, we just set U1 equal to V1, and we divide by the square root of the inner product of V1 with itself. So that means that the norm of U1 is 1. So it's normal.
Is that 0, comma, n, comma, basis UI?
This is orthonormal basis.
Orthonormal.
Ortho meaning, well, ortho means sort of straight, but it also means, in this case, perpendicular. Normal meaning normalized to unity. So these are vectors that are all perpendicular to, the u's are going to be perpendicular to each other and all of unit length. And this is a way of doing it. Okay, the next one, we start out defining little u2 as the second vector in the basis, v2, plus a coefficient, c1, 2, times the first vector in the orthonormal set. And then we require that this be orthogonal to u1. And so we take the inner product of u1 with u2, and this is u1 with v2 plus c12 u1 with u1, and what's this? u1 with u1. Huh? 1, yes, it's 1. And so this equation, since this is equal to 1, because it's, the thing is normalized, this equation says C12 is minus, we want this to be 0, of course. That's the whole point. We want the big U's to be orthogonal to each other. So therefore we have C12 is minus U1 V2. So in other words, this equation says that this plus C12 is 0, so C12 is minus that. So our U2 is V2 minus U1 V2 U1.
I'm sorry, that's like the one on the U.
Okay, where
The U, yeah, you've got
up, down, direct the finger.
minus sign, parentheses.
That's a minus sign.
Yeah, and then, no,
And that's a 1, yeah, you're right, a 1 and a comma.
Yeah.
Thank you. By the way, you asked a couple of questions. You didn't get any candy. You want candy?
I don't know.
No, okay. By the way, if you people shop at Costco, leave a note asking them to bring back Kirkland fruit snacks, which are tastier and healthier than these lousy Welch's snacks, but they're the best. Okay, anyway, so that's what U2 is, and now we normalize it. So we just say big U2 is little u2 over square root of the inner product of u2 with u2. So this gives us, now we have 2 orthonormal vectors. And I'll do one more and then you can see what the pattern is. We'll set u3 equal to v3 plus c13 U1 plus C23 U2. And now we want to say that U3, little u3, is orthogonal to U1. We want this to be 0. And so this is equal to U1 V3 plus, well, U1 with U1 is just 1, so this is C13, and U1 with U2, they're orthogonal. So this tells us right away that C13 has to be minus U1 V3. Similarly, we want U2 to be orthogonal to U3. Now U2, this would then be U2 V3, the first one, but this term vanishes because U2 and U1 are orthogonal. U2, capital U2 is normalized, so this gives us plus C23. So C23 is minus U2 V3. And so we have a formula for U3. U3 is equal to V3 minus U1 V3 times U1 minus U2 comma V3 times U2. And then we normalize it by just saying U3 is, capital U3 is little u3 divided by the norm of little u3. That's little u3. Okay, so that's how the thing goes. In general, uk is equal to vk plus a sum I equals 1 to k minus 1 CIK UI. CIK is equal to minus UI VK. And so little uk is equal to VK minus the sum I equals 1 to k minus 1 UI VK UI, and then big UK is just little UK over the square root of little UK, little UK. So this is one way to make a basis orthonormal. And an orthonormal basis is more convenient than one that's not orthonormal. Now, one thing that's surprising, yes?
I'm not completely clear on what the lowercase u's represent. I understand that uppercase are
well,
more
it's step one of the process. So step one is we say...
Is we just define them?
We define little u2 as big V2 plus some number times big U1.
Okay.
And big U1 is just V1 normalized.
Okay, so it's just a vector that we're defining that is orthonormal to U1.
That's right. That's right. Exactly. Little u2 is simply orthonormal to U1.
Okay.
And then after we have little u2 correctly defined, we normalize it. And then that's big U2.
So it is orthonormal to U1. It's not orthogonal.
Excuse me?
It's not normalized. So is it orthonormal or is it orthogonal to U1?
It's orthogonal.
Okay.
And when it's normalized, it's normalized. So let's see. You're entitled to probably about 4 of these. You need 1 4?
I'll take 2. That's fine.
All right, here's 2.
Thank you.
Did anybody else ask a question and not get a candy? Okay, so this Gram-Schmidt process is so orderly that one might imagine that if you take any basis and make it orthonormal, you get a unique set of vectors. But that's not true, and in fact you can see that if you take the original set of vectors, the v's, and instead of calling them v1, instead of starting with v1 and then v2 and then v3, you start with v4 and then do v1, then do v5 and then do v2 and so forth, you get a completely different set of capital U's. So you get a different basis. One way to see that immediately is, suppose you're in 2 dimensions and you have this is one vector and that's another vector. So one vector, v1 is 1, 0, and v2 is 1, 1. So v1 is normalized, v2 is not normalized, and these two are not orthogonal because they have an inner product that's 1. Now, if you did the Gram-Schmidt process starting with v1, this would be the first vector, and you'd wind up with a vector in the y direction as u2. So you get the vectors. You get this vector and presumably that vector. These would be the u's. On the other hand, if you started with v2, then your first u vector would look like this. It would be 1, 1 divided by the square root of 2. And your second vector would be perpendicular to this, so it would be off in this direction, and would be something like 1 minus 1 over square root of 2. Or it might be it might point, this doesn't point this, it might point down, I don't know, depending on the sign, I don't know how it would work out. But the point is that you get a different set of vectors, than the set you get if you if you enumerate, or denumerate, I don't know which it is, you enumerate the vectors v1, 1, 2, instead you go this way, 1, 2, and to Gram-Schmidt that way you get a different set of vectors. All right, now let me go to something that I mentioned briefly last time and mentioned more in the problem session, and that's the idea of an outer product. So we talked last time a lot about inner products, and of course inner products are something that you learn about a lot in math courses in college, but mathematicians, as far as I know, haven't, well, I shouldn't say I don't know what mathematicians do these days, but the idea of outer product is something that was brought into physics by Dirac, and I don't think the mathematicians at that, when he invented the outer product, I don't think they had a good notation for it. They knew what it was because, you know, linear algebra is sufficiently simple that any mathematician in a sense knows everything about linear algebra. But on the other hand, Dirac made a real advance. So let's suppose we have two vectors. F and G are vectors. And I want to define a linear operator. So linear operator that maps any vector H into F with a certain coefficient. And the coefficient is going to be the inner product of G with H. So in other words, AH is going to equal a number, GH, times the vector F. Or we can write it this way, F is GH. Since GH is an inner product, it's just a number in general complex. Now this is linear because inner products are linear. And so A on ZH plus WE is G on ZH plus WE times F. And so this is Z times GH F plus W times GE times F. So that shows that A is a linear operator. And if F, G, and H are vectors with components, Fi, Ti, Hi, then the ith component of the vector AH that the linear operator A maps the vector H into is a sum j equals 1 to n Aij Hj, and that's Fi times the sum j equals 1 to n Gj star Hj. Because this is the, or equivalently, this is Fi Gh. Okay, so I had in the handout and in the book, there are many examples of inner products. To save time, I just encourage you to look at them and study them. Maybe I will do one aspect of it, emphasizing Dirac's notation. So Dirac's notation was, suppose F is a vector ABC, and G is a vector ZW. So what Dirac did was he made just a sort of a notational advance of a minor sort just by saying F with an angle here and a straight line there is a column vector, and G is a column vector. These things he called kets. But what he did then was he introduced bras. So the bra associated with the ket F is A complex conjugate, B complex conjugate, C complex conjugate, and bra G is Z complex conjugate, W complex conjugate. And so now he introduced his way of writing these outer products was Fg is then ABC, and G was, G going this way was Z star W star. And so this thing is A Z star, A W star, B Z star, B W star, C Z star, C W star. And similarly, the ket G and the bra F, well, it's the ket G, so that's ZW, and the bra F is that. And so this is Z A bar, Z B bar, Z C bar, W A bar, W B bar, W C bar. Okay, that's Dirac notation. And it's become standard in quantum mechanics and in quantum field theory. And it just makes everything so much simpler. Let me just write the outer product of G with itself, this would be ZW, Z star, W star. So this is Z star, ZW star, WZ star, WW star. Did you guys see this in undergraduate math classes? Some of you did, some of you, all of you did? When I was a student, this wasn't mentioned at all certainly not in undergraduate math classes, or for that matter, classes that I took. And Dirac notation was, well, it was used in physics. All right, let's do some more Dirac notation. Once again, his way of doing things was, of course, really cute, because suppose you had a ket F, an operator C, and a broad G. So he would call this a bracket. Very clever. There's a story that he was once sitting in a waiting room and some woman on the other side of the room was knitting. And after waiting for, I don't know, 10 or 15 minutes for the doctor to call the next patient, who wasn't either one of them, he explained to the woman that there was another way of doing the stitch she was doing. I find that just amazing. You know, I don't know. I mean, of course, I never learned to knit, so maybe I'm more amazed than somebody who's been knitting a while was. But I think that what he did was he invented a new stitch, which he hadn't heard of. I don't know. I'm not. Okay, so let's look at what this, what a Dirac what this relation looks like in Dirac notation. It's just so much more natural. It's A on the ket H is equal to G H, the bracket, times the ket F. And now, you see this is just a number, so we can move this vector to the front, and then what we get is F G H. And now, one of the rules in Dirac notation, by the way, is if you have a straight line, you can add another straight line if you want. It doesn't make any difference. And consequently, you can write this as F G times the ket H. So in other words, the operator A, the linear operator A, is the outer product F G. So that's the advance that Dirac made. You see, in other words, the mathematicians previously could define A in this way, but it's kind of a certain, what requires a lot of brain work on the reader to understand what's going on, whereas Dirac's notation is just simply A is the outer product of the ket F, the broad G. And once you've written that down, everything else is automatic. Now this bra G is defined as the adjoint of the ket G. And the ket F is therefore defined as the adjoint of the bra F. And that's, of course, as it has to be, because the bra F is itself the adjoint of the ket F. And adjoint just gives you, is the same as not doing anything. So you get back to that. If you have an outer product such as Z, F, G, and you take the adjoint of that, then this is equal to Z complex conjugate ket G bra F. Okay, these rules, which are very simple in Dirac notation, explain most of the relations in quantum mechanics. At least the sort of relations that you have to go through a zillion times when you're computing things. When you're computing quantum mechanical amplitudes, quantum mechanical probabilities, all you really need to know, the key relation that you've got to, dare I say, memorize, is this. And the reason why this is all you need to know is that an outer product is the most general. Outer products form the basis for any set of linear operators. Linear operators, a given set of linear operators can form a vector space. A basis for that vector space is formed by outer products of kets and bras in the space on which the linear operators act, or spaces in which they act, and then complex numbers. So this really is basically the whole story. So let me illustrate that by writing a linear operator A as a sum on K and L, ZKL, KL. So I'm imagining that K is some, let us say, orthonormal basis. L is another orthonormal basis, or the same orthonormal basis, actually. I mean, this would be more convenient to make them the same. But they could be just any sets of bras and kets, and Z is an arbitrary set of complex numbers. Then the adjoint here is just sum on K of L, Z bar, KL, L, K. You see, I lapsed into something that I will often do unconsciously, is when you have here a ket on the left and a bra on the right, if you let the points touch, it becomes an X. And it's much easier to write an X than two things, right? So I often do that. That's code for what it is. Okay. So suppose we have a ket H that is A on F, and we take its adjoint. And the adjoint of that is A F adjoint. And now we're writing A like this, and so this is the sum on K and L, ZKL, KL. But now that L is hitting the F, so this is an F. And it's an inner product. And we're taking the adjoint of the whole thing. And then we just follow this rule what you do is you turn a ket into a bra into a ket, you complex conjugate all the numbers. And so this becomes some z bar KL FL K. Oh, I got the K wrong, damn it. Now let's see, did I do that right? I'm telling you it's all so easy, and if I get it wrong, it's not so great. Right, and another way of writing that then is that this is F a dagger. That is to say, if what happened to F? F was, oh yeah, right. Right, F a dagger. In other words, it's F on some Z bar KL LK. This is the same as that. You might rewrite it this way.
So you're saying that is the same as just that one component right there? The
Okay.
FL? You're saying that that's the same as FL, right?
Louder and...
When you put the equal to, are you saying that that's equal to only that component F and L and not the rest
Well,
of it?
this is equal to that, is equal to this, is equal to that. Everything here is equal.
So when you, that's exactly my question. Is it just F and L that's equal to that top part, or the whole thing?
The whole thing.
The whole thing.
This whole thing is equal to that whole thing, is equal to this whole thing, and that's the whole thing. Okay, so Dirac made everything automatic for us, and the number of his contributions to physics is just extraordinary. His fingerprints are over almost all of theoretical physics. Okay, let me go through a few more examples here. Oh, I'm a little leery about running out of time. Let's suppose that F is a sum CK K equals 1 to n. So the K, these are orthonormal. So this is an orthonormal basis for some n-dimensional vector space. We can express an arbitrary ket in this way, or we can expand an arbitrary ket in this way. And so now if we take the inner product of one of the basis vectors, so yeah, the orthonormal basis is K, L, and so forth. K and L are just integers here, integer labels. So then KF is the sum CK, inner product LK, and this is the sum CK delta, Kronecker delta LK, and so this is C sub L. So in other words, if we expand an arbitrary ket in terms of coefficients and an orthonormal basis, one of the useful things about the basis being orthonormal is that we can immediately identify the coefficients as CL is L, is the inner product of the orthonormal basis vector L with the ket F, the arbitrary ket F. And so the original expression F, which was the sum CK ket K, is a sum CK is then KF K. And now this is a number, it's simply a complex number, so we can rewrite this as K K F. Now, as I said, you can always add an extra line in Dirac notation. And you can put in parentheses, if you can squeeze that parenthesis between those two lines. And so then what you see is you have sum on n, outer product of the orthonormal basis vectors on f is the original vector f. So this must be the unit operator for the space. So in other words, the identity operator is the sum on n, sum on k, k, k. K equals 1 minus a to n. And we could have chosen a different basis. We could have expanded the f's in terms of some other basis. And what we would have found is, if we had used a different basis, we would have had something like this. Alpha j, j equals 1 to n, where the alpha j's just represent another orthonormal basis. Just a different set of labels for different bases. And we would then have two different representations of the identity operator, and we could write f not simply as, well, we just take this equation, multiply by the right, from the right by the ket f, and we get f is I times f is sum k, inner product of k with f, and then up here it's the sum alpha j, inner product of alpha j with f. So these are the basic rules that Dirac, of linear algebra and quantum mechanics, that Dirac has made easy for us, at least easy once you've gotten used to them. Okay, there's a this example 1, 2, 4, I'm going to do this in the problem session because we just can't do everything in class. That's an important example, though. If you skip the problem session, study that example, and that example shows you how Dirac's notation is so much better than the more cumbersome conventional notation that I used when I first explained change of basis a few sections ago on Tuesday. No, I somehow lost my place. Really lost my, oh, there we are, okay. All right, so there are a bunch of examples here, 3 different examples. So I'll do one of them in class. Remember we talked about inner products on Tuesday. Let me show you the rules for an inner product in Dirac's notation. And this is a positive definite inner product. Well, it's that FG is GF complex conjugate. It's that F on Z1 G1 plus Z2 G2 is Z1 F G1 plus Z2 F G2, and the first two imply the third, so this is just a consequence of the first two. Z1 F1 plus Z2 F2 G it's just basically the complex conjugate of this equation. Z1 complex conjugate F1. Well, it's not really the complex conjugate because the notation is a little bit different. F1G plus Z2 bar F2 G. And then the third in Dirac notation, the last one, is that this is greater than or equal to 0 and FF equal to 0 implies the ket F vanishes. Okay. So, when mathematicians often think about linear operators and vectors as abstract quantities, but when we as physicists need to actually do computations, and so we need to represent vectors and linear operators in terms of numbers and arrays of numbers called matrices and so forth. And in other words, the coefficients Fj are the inner product of J with F, and say Gj star is the inner product of G with an let us say an orthonormal basis J, and we would say then that GF is G, the identity operator, which I'm just going to write as the sum of outer products. And so this is Gj star of J, and similarly GAF is G identity A identity F. So it's very useful to just stick in identity operators, and you write the identity operator as a sum of outer products of an orthonormal, of the states of an orthonormal basis, or of the vectors of an orthonormal basis. And so this is then G, J, J, A, K, K, F. And so this is then Gj star, AJK, FK. Of course, here summed over J and K in both cases. Sometimes I forget and use a generalization of Einstein's summation convention. Einstein pointed out that people could simplify his equations if, whenever he had something like AI, BI, summed over I, that he would just write AI, BI for short. And if you had two indices that were the same, one upper and one lower, it was this sum. And in particular, he was working in 3 dimensions, so it was 0 to 3 or 1 to 4. I'm sorry, working in 4 dimensions, 4 space-time dimensions. So this was the Einstein summation convention. If you want to know the difference between upper and lower indices, go to the chapter on general relativity. I want to skip that for now. But in physicists just love getting rid of these summation symbols, especially if they're typing their own papers in LaTeX, which we often do. And so basically, any index that's repeated is summed over in almost any physics paper. So this is the same thing as Gj star, AJK, FK, and the idea is you sum over J because it's repeated, you sum over K because it's repeated, and you sum over however many indices, however many there are of each index. And that's normally obvious from context. So sometimes I will forget to write the summation symbol just because I'm used to that notation. It's also obviously simpler. One can write these vectors in various ways. You can write them as 1f dot 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 nf, or you could write them as f1 fn. So that's actually what we mean by a vector, or for that matter, a ket. Well, the ket is abstract. This is a representation of the ket. This is a representation in terms of a particular basis. You use a different basis, you have a different set of complex numbers. So let's see, I forgot to erase that board. I normally do it last because this board was broken by one of our former chairmen, and he replaced it with a cheap blackboard, and so I use it only if I run out of the normal blackboards. I keep forgetting that I almost always do run out of the normal blackboard. So I should just go ahead and erase it and be done with it. So if you have here an expression, GAF as this, I was using a basis that I called J, or equivalently K. If instead I had used a different basis, then we'd have a similar set of equations. In other words, we'd have GAF. I could insert as the identity operator a sum alpha j, some different set, and then A, and then another sum, well, I said alpha k in this example. So that's another way of expressing this, and then this would be, well, it would obviously be just the sum of jk of g alpha j a alpha k alpha k. So, so this trick of writing the identity operator as a sum of outer products of orthonormal basis vectors, and you can choose any set you want as long as they're an orthonormal basis for the vector space. The trick of inserting that identity operator anywhere, this is always justified, and it often clarifies what you need to do in a particular problem. Let's just notice one other feature of Dirac notation that's so very nice. Namely, suppose we're changing from one basis to another. So here are outer products of, let us say, orthonormal basis vectors. but they're two different bases. This is the K basis, this is the alpha K basis. This is then a unitary operator, and in fact that you'll hear in quantum mechanics and quantum field theory unitary operators used. Every unitary operator is simply a change of basis. And every change of basis from one orthonormal basis to another orthonormal basis is automatically a unitary operator. That's important to know. And Dirac's notation makes it pretty clear. And let's see what happens to U sub L. U sub L here is a sum, alpha K, KL, but these guys are orthonormal, and so this is alpha K, Kronecker delta KL, and so this is alpha L. So U, the unitary operator, takes us from one basis to the other basis. So previously I said that the most general linear operator is a linear combination of complex numbers times outer products, and that once you define adjoint in this way, then that demystifies the adjoint symbol, which can be very confusing actually in some quantum mechanics textbooks. Once again, if you insert...
Question?
Is there a question? Yeah.
A line instead of the bracket thing at the end of K.
Where, which line? This
Down
one?
here, at the bottom.
This one?
The bottom line, at the end.
Oh, you're right. That's screwed up. Thank you. This should be a straight line. You don't want any candy. Anybody else? All right. Let's suppose that we have this most general linear operator. So then it's going to be a sum on K and L of K, K, A, L, L. So notice I lapsed into my shorthand, my X shorthand. But also, notice I've just multiplied A on the left and right by an identity operator. And now if we take the adjoint of that, well, what is it going to be? It's going to be a sum LLA KK. Whoops, sorry. On the other hand, using our rule here, this thing is a sum L K A L complex conjugate K. And so now we get the important relation just directly from Dirac notation that L A dagger K is just K A L complex conjugate. And so the matrix that represents the adjoint is, this is A dagger LK, and this is AKL complex conjugate. There's a typo. I wrote LK instead of KL in the book. That was a mistake. So we want to change that. And now, what is AKL? Well, this is a transpose complex conjugate LK, because when you take the transpose of a matrix, you interchange the row and column indices. So in other words, if you have a numerical matrix, the LK, let me write this a little more clearly. I can find a nice little eraser. So let me just make this a little clearer. Oh, I made it worse. A adjoint, KL, is a transpose complex conjugate, LK, damn it. So this is the LK matrix element of the operator Adaga, or the LK element of the matrix Adaga, and it's also the ALK element of a transpose complex conjugate. So those are important relations, and as I said, I had the L and K interchanged in the last two expressions of equation 1.161. You want the correct versions on the blackboard. So there are a zillion, there are several more relations on this well, maybe I should go through them just to so let me erase here to make more space. Why don't you guys tell me, do you want me to, have you had enough of this Dirac notation and I should skip on to the next topic, or do you want me to do a few more examples? Well, I'm terrible at reading minds, and my wife says that I'm terrible understanding what she means when she talks. So you've got to tell me very clearly what you want me to do. No, all right. Okay, so let's. All right, I tell you what. I will do the rest of this section in the problem session, and I'll go on to self-adjoint for hermitian linear operators. Well, notice that I've been focusing here on the adjoint of an operator. There are some special operators that are very important in quantum mechanics, such that the adjoint of the operator is the operator itself. Well, in that case, this relation would be A transpose complex conjugate LK would be a dagger LK, but a dagger would be the same thing as A, so this would be ALK. So this is a matrix that, if you take the complex conjugate of the transpose, you get the same thing. And this is called a hermitian or a self-adjoint matrix. It's named after Charles Fourier. In such a case, then, AKL, which is KAL, is equal to K a dagger L, and this is L A K complex conjugate, because that is a transpose complex conjugate K L, and this is a dagger KL. Okay, so these are the relations that hold in this case, and we can also write GAF as AG, F, or F, AG complex conjugate, or FAG complex conjugate. So these are all various ways, various relations that hold for matrices that are hermitian. And there are certain kinds of operators that are automatically hermitian. So, if a matrix is real and symmetric, then it's hermitian. If it's imaginary and anti-symmetric, then it's automatically hermitian. But of course, if something is real and symmetric in one basis, it needn't be real and symmetric in another basis. And if something is imaginary and anti-symmetric in one basis, it needn't be imaginary and anti-symmetric in some other basis. But if it's real and symmetric in one basis, then it will be hermitian in every basis. So hermitian is a property of the operator. Being real and symmetric, or imaginary and anti-symmetric, are properties of the matrices that we use to represent the operator in a particular basis. Now, an important feature of hermitian operators is that if you have an eigenvector of an operator that is hermitian, then this thing here is real. So the eigenvalues of a hermitian operator are real. We'll see that in section 29. There's something about Fiert's identities. I'll also put this in the problem section. Now, of course, if you have real symmetric linear operators, things are a little bit simplified, and the notations, section 15 discusses them. I think you can just read that. So I'll start next time with unitary operators, and go on from there. So, are there any questions? Okay. Normally we have a colloquium on Friday, but the scheduling of colloquia this year has been screwed up, and so we don't have any colloquium this Friday. As I said, come see me if you want to ask questions. I'm typically in my office after 4, actually 7 days a week. But not at night. I leave at about 7 and or 6:45, and I normally don't come back. So it's sort of a 3-hour window there. You can also send me email, and if you become a contact on my iPhone, you can call me up. But do call late in the day. You could call at night, though, but not too much. All right, I guess that's. Why don't you push the button?